Good morning, everyone. I am K. Narsimurthy, presently working as an assistant professor in Government First Grade Women's College, Tumkur. So, I am presenting a video in the subject physics, and this is my 34th video for second semester students of Tumkur University. The topic which I am discussing today is hysteresis curve. Okay, this comes in the chapter hysteresis will comes in the chapter magnetic materials. This is a new chapter which I have started from the 31st video, means the three videos back. So I have explained about the magnetic materials. I have explained very basic terms: intensity of magnetization, magnetic induction, and the permeability and the susceptibility. And these are some of the very basic definitions which I have explained in the first video of the third unit, which is 31st video. And after that I have explained the magnetic materials completely. Three types of magnetic materials: diamagnetic, paramagnetic, and ferromagnetic materials, and their unique properties. I have discussed their properties of these three magnetic materials and how they are different from one another in their properties. Right after that, I have discussed a very important theory, which is Langevin theory. This Langevin theory is little bit beyond your BSc concept. Little tough topic, lot of equations, very less theoretical understanding. So after that, I am discussing this hysteresis. I told you this ferromagnetic material will shows the hysteresis. I'll tell you what is this hysteresis is. Okay, let us start with this topic, hysteresis. The concept of domain was actually introduced to explain a ferromagnetic material. Okay, so this is used to explain the hysteresis also. The concept of magnetic domain, as I told you, is material has been divided into domains, and in each domain the dipoles are oriented in one direction. But if you take from one domain to another domain, the direction of dipole will be different. They are randomly arranged. When a field is applied, these dipoles means the dipoles in the domains are start aligning in the direction of the magnetic field, and this gives us the net magnetization. When field H is increased and decrease to its original value, suppose if I increase the field H and I decrease the field to the original value, the domains do not come back to their original configuration. Earlier it was very randomly oriented, and when I applied a field H, this orientation they starts orienting in the direction of the magnetic field. Then if I decrease the field, what happens is they will not come back to its original configuration. They will not come back to the original randomness. And this lack of retraceability, they are not retracing the exact path. They are not going exactly to the same position. They are not going exactly to the original configuration. So they are in a lack of the retraceability. The lack of retraceability of magnetization curve becomes, because of retentivity, because of it retains something. It retains something, even though the field is completely removed. It retains something. It retains some orientation, and this is called hysteresis. What is hysteresis? The lack of retraceability of magnetization. Okay, even the magnetic field is reduced, the magnetization will not go back to its original configuration, to its original position. There is a lack of retraceability. It is not retracing exactly the same path how it is raised. So magnetization is raised, okay, when your field is increased, but when your field is decreased, it is not exactly retracing the path. There is a lack here. This lack of retraceability of magnetization curve. Because of this property called retentivity, is called the hysteresis. So with these ferromagnetic material will have a special kind of property which is called retentivity. Because of this retentivity, they will not retrace the path, magnetization path exactly. Therefore, there is a lack in retraceability of the magnetization curve because of the special property which is called retentivity, and this whole process is called the hysteresis. Right? We'll see this curve here and we'll understand things better. Now we have plotted a graph of magnetization versus magnetizing force. The x-axis I have a magnetizing force. Okay, I am applying a force in terms of magnetic field, and y-axis is the magnetization. And see what will happen. Okay, when external magnetic field, this is magnetizing force, is applied to the ferromagnetic material, we know it is magnetized. Okay, it is strongly magnetized in fact, and that means it is magnetized. In a sense, all these magnetic dipoles orient in the direction of the fields. Okay, so what do you mean by this magnetization? So meaning of magnetization means all the small dipoles which are present in the different domains, they start orienting in the direction of the magnetic field. That is what the magnetization is. When external magnetic field is applied, they start magnetizing. Ferromagnetic material get magnetized, means all magnetic dipoles orient in the direction of the field. Suppose if H is increased, the dipole starts orienting in the direction of the field, and magnetization increases non-linearly. Be careful, it is not a straight line. So magnetization is not a straight line. It will not increases linearly with the magnetizing force. The magnetization will not increase linearly with the magnetizing force, but it is a non-linear. It is a non-linear. I'll show you how it is non-linear. Look at the curve. Look at the curve FA. As magnetizing force increases, this magnetization also increases. Do you find any straight line in an FA? FA seems to be a curve. FA is a curve. It is not a straight line. So there is no linearity. Means the magnetization is not linear with the magnetizing force. So it is not linear because the curve clearly shows that it is not linear. At a particular point, all dipoles are oriented in the direction of the magnetizing field. Okay, and magnetization becomes maximum. You go on increasing the magnetizing force, they start magnetizing, and at one particular point, all the dipoles will completely oriented in the direction of the magnetic field. That means it is full. It is complete. Magnetization is complete. And it attains a maximum value. So magnetization becomes maximum. And this is called saturation magnetization. I will show you in the curve. The saturation magnetization is at point A. As you increase magnetizing force, the magnetization increases and attains a maximum value. That's the point A. It increases from F to A. It increases to a point A, which is called saturation magnetization. The point A is called saturation magnetization. Right. We'll see after what happens after A. In the figure, the point A represents saturation magnetization and the curve OA represents the magnetization curve. This OA is the magnetization curve. Right. We have increased magnetizing force. Magnetization increases, attains maximum, which is called saturation magnetization. Right. Suppose if I start decreasing this magnetizing force, magnetic field, if H decreases, the material should get demagnetized. Material gets magnetized slowly but not follow the path AO. Instead it follows the path AB. Okay. Look at the curve. If I start decreasing the H, if I start decreasing the magnetizing force, the curve will not going back in a same path. The curve is retracing some other path. The some other path is AB. Instead of it is going back in a path AO, it is going in a path AB. So this is entirely different. This is entirely a unique phenomena which is exhibited by the ferromagnetic material. Instead of going in a retracing exactly the same path, it is going in a different path and it is retracing the path AB. Right. Next, when H equals to 0, when magnetizing force is 0, then we expect actually the magnetization to be 0, but actually it is not 0. Magnetization is not 0, even the magnetizing force is 0, even the H is 0, the magnetization is not 0. It has some non-zero value, and this is known as remanence magnetization, or it is called the retentivity. This is what the retentivity. Retentivity gives rise to permanent magnetization. So we are decreasing the field, we are making the field 0, but still we have some magnetization left in the magnetic material. They have some non-zero magnetization, and this is known as retentivity, and retentivity is what the permanent magnetization. Okay, right. Suppose, okay, I have made this field 0, I have made the magnetizing force 0, but still M is not 0. Let's see, I am keep on decreasing the field. I am going in a negative direction. I am going H in an opposite direction. I am applying H in an opposite direction. Let's see what happens to the magnetization. The magnetization decreases and becomes 0 at some point. Okay. So at some point the magnetization becomes 0. The reverse magnetizing field required to demagnetize the given ferromagnetic material completely is called cohesivity or cohesive field. The magnetizing field which is required to demagnetize a given ferromagnetic material is called the cohesive field. You can look with the figure. So it is very clear from the figure that if you go back, if you decrease the magnetizing force in a negative direction, look at the curve, look at the behavior of curve. The magnetization is going down and it is attaining 0 at one particular point, and this field, this magnetizing force is what is called cohesivity or cohesive field. This is the field which is actually required to bring the magnetization to the 0. Okay, so this field H which is required to make this magnetization 0 is called cohesive field. Right. Yeah. Now, if H is increased in same direction, I am going further in a negative direction. What happens? The magnetic material gets saturation magnetization in an opposite direction. First it was going in a positive direction, it attains saturation magnetization in a positive direction. But whereas now if I further increase the magnetizing force in a negative direction, this magnetic material gets a saturation magnetization in a negative direction, in an opposite direction. It was shown at the point D clearly in the graph. And this closed loop A, B, C, D, E, F, A, this loop is called the hysteresis curve. Now we have gone one round in a loop, we have increased, decreased, and we have gone negative, and we have gone further negative, and we saw how these magnetization behave in a ferromagnetic material. It completes a one curve, one loop, one closed loop, and this closed loop is called the hysteresis curve. Okay, fine. Right, after understanding this hysteresis curve with the help of that clear diagram, we'll go to the energy loss due to hysteresis. Now we'll see what actually the energy is losing in retracing a one complete curve. Right, when magnetic material is taken through a cycle of magnetization, cycle means one's complete loop, the energy is spent in aligning a magnetic dipoles, and this energy cannot be recovered completely on reversing the magnetic field. As you have seen in the diagram that you cannot recover the energy completely even if you are reversing the magnetic field. Okay, right. Right, there is some loss here. There is some loss. There is some energy loss here because energy cannot be recovered completely even after reversing the magnetic field. Right. This loss of energy per unit volume per cycle due to the hysteresis is equal to the area under this BH loop. The area within that loop will gives us the loss of energy per unit volume per cycle, and this is actually called the hysteresis loss. So there is a loss in energy. This loss because energy cannot be recovered completely on reversing the magnetic field, and this loss per unit volume per cycle in an hysteresis is what equal to the area of that loop, and this area of the loop is the hysteresis loss. And we'll find out an equation for hysteresis loss. Now we have considering a magnetic material having n dipoles. So we have n dipoles, and let m is the magnetic moment of each dipole. When material is placed in a magnetic field H, this dipole starts orienting. This dipoles makes an angle theta with the magnetic field, which makes an angle theta. Now this magnetic dipole started aligning in a different directions, and which makes an angle theta. Now if I look for the magnetization along the direction of field, if I look at the direction of field, it may not be completely oriented in the direction of the field, but if we look for the components of that in a direction of the field, it will be m cos theta, component of the dipole along the direction of the field, because the dipoles may not exactly in the direction of the field. It is making some an angle theta. No, fine, it's okay, it's making some angle theta. It may not be completely magnetized, fine, but we look for the component of this dipole along the direction of the magnetic field. It will be m cos theta. That's what the magnetization is. So if that is for an individual dipole, it is made up of large number of dipoles. We'll take the sigma, we'll take the summation of all these dipoles to get a total magnetization of this ferromagnetic material. And we don't find any component of this in the perpendicular direction. We are considering only horizontal component, since there is no magnetization perpendicular to the direction of the field. So we are considering only the horizontal component. Now the variation in the magnetization with respect to theta, I am looking for the variation. Now variation will be dm, very small thing, dm, which is equal to, if I differentiate that equation 1, it will be minus sigma m sin theta into d theta. So cos theta differentiation will be minus sin theta. Right. Now let me find a torque which is acting on this dipole. We know the equation for the torque acting on the dipoles. We have derived this equation in the previous videos. Tau is equal to m crash b. Tau is equal to m crash b, and that is equal to sigma mb sin theta. If you find any cross product, you write sin theta. If you find any dot product, you write cos theta. Very simple thing. So m crash b will be mb sin theta, and we have a sigma over there. It's because of I am considering all the dipoles. Sigma indicates that I am considering all the dipoles. This is the torque due to all the dipoles. Now if I find out the work done by a field in aligning these dipoles, dw is equal to minus tau theta. Minus tau into t. It's just like force into displacement. Work is force into displacement, whereas in the case of rotation, it is tau into d theta. There in the linear motion, work is force into displacement, f into x. Whereas here, instead of f, I am writing tau here. Instead of x, I am writing theta here, because this is a kind of rotation. This is a torque which is acting on the dipole. The dipole is actually rotating, not displacing. The dipoles are orienting, means the dipoles are rotating. Therefore, I am writing this dw as tau into d theta. So therefore, it is, if I consider all the dipoles, it is minus sigma. Tau is what? The minus sigma mb sine theta into t theta. Now I know what is B is. I can relate the B and H, magnetic induction and the magnetizing force, which is equal to B is equal to mu naught H. And if I substitute for B, so work done, the small work done is equal to minus sigma m. Instead of B, I am substituting mu naught H, m mu naught H sine theta d theta, equation 4. Now if from equation 2 and 4, go back and see what is equation 2 and 4. 2 is the dm equation and 4 is the dwo equation. If I see these two, I can get an equation dw is equal to mu naught h into dm. I have substituted for dm. Okay, I have write the dm in the right hand side. So that gives the equation 5. Now work done by the field per unit volume of the material for one complete cycle. Now I am looking for the work done for one complete cycle. If I look at that, it will be a line integral. It will be a line integral of mu naught h dm. It is a one complete cycle. So therefore I am doing a line integral of this mu naught h dm. Mu naught is anyway constant, permeability of free space. Take it out. So integral of h into m. So line integral of h into m is something like a curve of h and m. Curve of h and m. Therefore, hysteresis loss is equal to the mu naught times mh curve. The work is what? Actually the energy. Work is nothing but the energy. This energy is what we lost in the hysteresis. So this is the hysteresis loss, which is equal to mu naught times the area of this mh curve. Okay, right. So a line integral h and dm will represent that is the area between these hm curve. Okay, so if that is multiplied by mu naught, you will get the work done. You will get the energy which is lost during the hysteresis. Right. We'll further substitute and see what will happen. I have a magnetic flux density equation, B equals mu naught into H plus M. Change the magnetic flux density. Change in magnetic flux density, I can differentiate that dB equals to mu naught dH plus dm. So dm equals 1 over mu naught dB. I have rearranged this and see, because I want an equation for dm. So dm is equal to 1 over mu naught dB minus dH. Let us call it as equation 7. On substituting 7 in equation 6, which is work done equation, which is an energy loss equation, instead of dm, h into dm, I am substituting 1 by mu naught dB minus dH. If I go further, W is equal to line integral of h dB minus mu naught line integral of h dH. Now what is line integral of h dH? H and dH are in the same direction. They are in a straight line. There is no loop at all. If there is a loop, that area of that loop will give that. If there is no loop, it is a straight line. It is not a curve, it is a straight line, because h dH is a straight line. So you cannot expect any loop, and if we do a line integral of that, it will be 0. And we are remaining h dB in the right hand side. So work done is equal to line integral of h dB, which is the area of BH curve, BH loop. So work done or an hysteresis loss is equal to area of that BH loop. You can say the hysteresis loss in two ways. One is the hysteresis loss is equal to area of the BH loop, or you can say the hysteresis loss is equal to mu naught times the area of the MH curve. Whichever is convenient, you can say it in two ways. Either way is okay. Right, we have discussed the hysteresis loss. So this is the BH curve. Okay, so area of the BH curve. is what actually the hysteresis loss. The area, exactly what area which is tracing, the area inside the loop will gives us the hysteresis loss. That area region PQRS gives the H into dB. So that area PQRS will gives us the H into dB. Okay. Thus, it's clear that the net energy dissipated per unit volume of a material during a complete cycle of magnetization is equal to the area ABCDEF or area of BH curve. Okay, therefore, energy dissipated per cycle of magnetization will gives us this equation. This is the equation of energy dissipated per cycle. It is energy dissipated per cycle, which is equal to line integral of h dB, which is area of BH curve, or mu naught times the area of MH curve. Okay, right. So these are the some of the books which I have referred. You please go through these books. You will understand things better. Thank you.